if you take a look at this definition right here, it says f of x is defined to be on a closed interval AB, and P is a regular partition. For us, that just means we chop it up into equally spaced pieces. Delta x is the width of each subinterval. And then for each point, xi star is some point in the subinterval. So if we use the left endpoint, we use xi minus 1. If we use the right endpoint, we use xi. A Riemann sum is defined to be the following. So we've already been using this. I told you it was called the Riemann sum at the very beginning. But basically, we're saying this. Your delta x is equal to b minus a over n, right? This is the width of each rectangle. And your Riemann sum of, let's say, xi star is a sample point. Then the Riemann sum is equal to the sum as I goes from 1 to n f of xi star times delta x. So this is the height. This is the width. So this is what all we've been working with so far. Okay. Actually, I'm going to hold off on the 4.2. Let me the thing that I wanted to show you was this next point right here. This is an approximation for the area of a curve, but how do you find the exact area of the curve? So this is an approximation of the area. But if you wanted the exact area, what you do is you would take this finite sum here and what you would do next is you would take the limit as the number of rectangles goes to infinity. Okay. So I can show you a graphical example. Desmos, Riemann sum. Here we go. So if you take a look at this picture, you see that we have red blocks and we have green blocks. Those of you that have watched the 4.2 video, do you guys know what the difference is between the red blocks and the green blocks? Does anyone want to take a guess? You want to? Terry says plus minus. Can you be more specific than plus minus? I think you get it, but what does plus minus mean? Anyone? Negative and positive areas. Ah, yes. So if the function is above the x-axis, then it's going to be a positive area. That's all the green parts. If the function's below the x-axis, then those would be the red parts. So we call that signed area. So since this is our first time seeing it, I don't really want to mess with signed areas. So let's just only look at the green part. So let's move A to 0, and let's move B to 2. And then now we only have green area. Okay. So if you look at this picture right here, the region that we're concerned with is 0, 2. That's your AB. And your function is this crazy sine of 2x plus x over 3. So you can see that at the top left part there. And if you look near the bottom, you have this n here. That's the number of rectangles. So what I can do is I can hit the play button. And if I hit the play button, it's going to start to cycle through the different values of n. So let's hit play and see what happens. So let me pause this. So what do you notice? You start with a very small number of rectangles. Like here we have 5 rectangles. You get a very poor approximation. But if I go all the way to 91 rectangles, this picture looks like a very good approximation of the area. And this only goes up to 100, but as we know, we're taking the limit as n goes to infinity. So you can imagine an infinitesimally narrow rectangle. And when we have such a narrow rectangle, there really is no difference between the left endpoint and the right endpoint. So if you take the limit as n goes to infinity, it really doesn't matter which endpoint that you use. So really, that's how we can say, oh, the actual area is just going to be the limit of the Riemann sums. And it doesn't matter if you choose the left endpoint or the right endpoint. Okay, so that was the purpose of this demonstration. Now I want to point out something. There is this requirement that our function is continuous. And why do we need a continuous function? We don't really want a jump discontinuity within our interval. Because if there's a jump discontinuity, there could be a big difference between the left endpoint and the right endpoint. But when your function's continuous, as you make it narrow, there's not going to be hardly any difference between the left endpoint and the right endpoint as far as the y values go. So that continuity is really necessary to distinguish between those cases where you have this jump discontinuity, and then it made a difference if you chose the left or the right. Okay. So that's really 4.2, but we sort of introduced that idea right here. So let's take a look at example 7 together, and let's see how this goes. So for this guy, we want to right sum because they're asking for R4, so that's a right endpoint. And they're telling me that the number of rectangles we have is going to be 4. Okay. And then they also give us the function value, the function and the two, the A and the B. So let me draw a graph. And let's label our points. So here's 0, here's 1, here's 2. And let's label this axis. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. Here's 10. So when you look at our function, this is basically a quadratic function, right? So x squared looks like this. When you flip it, multiply by -1, it opens downwards. So if that's the origin, you're going downwards like this, then you got to go up 10 units. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you get a parabola that opens downwards, and its vertex is at 0, 10. So if I had to go to graph this guy, sorry, the graph looks something like this. Here's the vertex 0, 10, and it comes down like this. Something like that. Okay. I wish I hadn't drawn my graph so accurately because there's this large vertical space here, but what can you do, right? So because this is chopped up in 4 intervals, I'm going to cut it in half first. That's going to give me a 1.5. I cut it in half again. That gives me a 1.25. I cut that in half again. That gives me a 1.75. So the first step is always chop it up into, chop the interval up into pieces. That's called the regular partition. Okay. Then the next thing I want to do is I want to find my delta x. My delta x is b minus a divided by n. That's 2 minus 1 divided by 4. That's equal to 1/4, or 0.25. So that's how we could see that each of these rectangles here have a width of 0.25. Does that make sense for everybody? All right. Next, I want to draw my rectangles. So see if I can do a decent job here. No, it didn't work. Oh, that's not bad. For me, those lines actually look parallel. It's like a miracle. And then we want to form our rectangles, right? And in this case, we want the right endpoint. So for the first rectangle, if I evaluate the right endpoint, that's the height there. Second one, the height's there. Third one, the height is there. And the fourth one, the height is there. So this picture sort of represents our right endpoint approximation. Okay. So I'm still going to kind of stick with the same style I did before. The area is approximately equal to the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3 plus the area of rectangle 4. And we just need to figure out what each of those things are. So we know we're going to have f of something times the width, which is 0.25. What number would you put in here first? Any thoughts? What number would you put there? Terry, 2 would be over here, but we're looking at the first rectangle right here. So I want to evaluate. At a point. Can you guys all see that we want to evaluate at 1.25? That's the right endpoint of the first rectangle. So this is going to be 1.25. When I do the second rectangle, that's going to be f of the next endpoint, which is 1.5 times 0.25. For the third rectangle, that's going to be f of 1.75 times 0.25. And the last rectangle is going to be f of 2 times 0.25. Does that make sense for everybody? Is there any questions about this? Okay, cool. So I'm going to change the way this looks. I'm going to do it slightly differently this time. You see how every single term has the 0.25. So I can factor out the 0.25. This is 0.25. And then this is just going to be f of 1.25 plus f of 1.5 plus f of 1.75 plus f of 2, like that. So, so now we're going to evaluate what each of those things are. This is 0.25 times 10 minus 1.25 squared plus 10 minus 1.5 squared plus 10 minus 1.75 squared plus 10 minus 2 squared. And when you get that, you are going to get, you stick all that into your calculator, you're going to get 7.28125 units squared. Okay.